Hello, my name is Talal Abdalla. I'm a PhD student in Computer and Control Engineering. In this brief video, I'm going to highlight my research work that I completed throughout my career here at Polytechnical. So, the main framework that I'm working on is identification and control of linear time varying systems that are affected by bounded measurement noise. So, let us now go together through the addressed problem.
So the general problem is control of dynamical system. So assuming that we have a linear system that is time invariant, we can deploy classical control approaches, such as, for example, PID and its variants and pole zero placement technique. But now let us look at the more realistic case, which is when we have noise induced in the feedback loop. And this is due to the fact that we are using a sensor to measure the control output. In this case, we can use both control techniques that assure noise rejection through proper design. Some of the techniques worth mentioning here are H-infinity and model predicted control. Now, what if the plant is no longer time invariant and actually its dynamics change over time? In this case, a fixed controller may not be capable of maintaining desired performance and over time will lead to instability, which is something you want to avoid when designing a controller. In this case, we need to design an adaptive controller that can cope up with the variations in the plant and assures the closed loop behavior is the one we desire. Also, again, we have noise entering the loop, which will introduce uncertainty, and if not properly accounted for, will lead to unwanted behaviors. So, to address this, we come up with techniques that allow us to account for the varying plant and the noise induced in the feedback loop. We rely on set membership identification techniques, where the uncertainties are assumed to belong to a given set. And in return, we define what is known as the feasible parameter set, which is the set of all parameters consistent with the measured data, model structure, the bounds on the errors and variation. So here, what we do is we compute upper and lower bounds on each of the system parameters, which are known as the parameter uncertainty intervals, that 100% include the true parameter.
In my thesis work, we addressed the problem of computing the parameter uncertainty intervals for single input, single output, and multi-input, multi-output linear time varying systems. We then develop a novel adaptive control scheme for controlling LTV systems. First, let us go through the set membership system identification for time varying systems.
So we developed a novel scheme for estimating the parameters of single input, single output LTV systems when both input and output data are affected by bounded noise. The proposed scheme assures fast convergence to the global optima, and as highlighted earlier, the true parameter always belongs to its uncertainty interval. The computation time is very small, 1.5 milliseconds to compute the intervals for a system with 4 parameters. Another point worth highlighting is that the algorithm can estimate parameters that change sign. Okay, we also address the more challenging problem, that is when the parameters may jump. And as seen here, we are accurately detecting the jumps and computing the uncertainty intervals in the presence of these abrupt changes. Also, the case of multi-input, multi-output LTV systems is considered, where here, in order to simplify the identification problem, we propose an approach to break down the MIMO system to solve the problem with less computation requirements or efforts.
Now we showcase the adaptive data-driven control scheme for controlling LTV systems.
So the starting point for this work is that we always assume that we do not have any information about the plant to be controlled. We design the controller by matching the plant output to that of a reference model that describes the desired input-output behavior. The approach is both fast and robust, and to compute the controller parameters, we compute those parameters that correspond to the minimum variation on all of the controller parameters. So here we can see the performance of the closed loop output, and we noted that with the presence of high sensor noise, the matching is satisfactory and meets the desired performance requirements.
I hope I managed to give you a clear idea about my research work. Thank you very much for your time and attention.